Hello everyone, this is Syed Afrit from the section of DAML. My roll number is 24951A66N9. The course title is Design and Analysis of Algorithms and the given topic is Parallelism in Tape Sorting. First we will see what is parallelism in tape sorting. So first of all we will learn about the brief verification of introduction to the topic, that is introduction to tape sorting and parallelism. Here, the tape sorting is a method used to efficiently organize large datasets stored on sequential access devices like tapes. Parallelism in tape sorting involves performing multiple sorting operations simultaneously to improve performance. Understanding parallelism is essential for optimizing large-scale data processing systems using tape sorting. So first in this diagram we can see that after each iterations minimum is placed in the front of your unsorted list, that is 2, 12, 10, 15 and 20, that is called swapping, and for each iteration indexing starts from the first unsorted element. Step 1, 2, 3 are repeated until all the elements placed at the correct position. So we will see understanding parallelism is essential for optimization large-scale data processing systems using tape sortings. So next we have historical context of tape sorting. In this we have tape sorting has been used since the early days of computing to handle massive data volumes. Traditional tape sorting was sequential and often time consuming, leading to the need of parallel techniques. The development of parallelism has significantly reduced sorting times and increased throughput on tape systems. The next is basic concepts of parallelism in data processing. Here we have parallelism involves dividing tasks into smaller units that can be processed concurrently. Effective parallelism requires careful partitioning of data and coordination between processing units. In tape sorting, parallelism helps mitigate the sequential access limitations of tape drivers. The next we have challenges of tape sorting, that system tape drives have high latency and sequential access constraints that hinder random data access. Data transfer bandwidth can be bottleneck in tape-based systems. Managing parallelism over tapes requires addressing these inherent limitations efficiently. Types of parallelism in tape sorting. Read and write parallelism involves concurrent data transfer operations across multiple tapes of drivers. Computational parallelism refers to running multiple sorting algorithms or phases in parallel. Data parallelism distributes data segments across processors for simultaneous sorting. Next we have tape partitioning strategies, dividing large datasets into smaller segments, allowing parallel processing on multiple tapes. Partitioning must be balanced to prevent bottleneck caused by uneven data distribution. Proper partitioning enhances concurrency and overall sorting efficiency. So we have partitioning and dividing and conquer. Partition, divide, compute and merge. Example applications: summing numbers, sorting algorithms, numerical integration, the n-body problem, bucket sort, adaptive quadrant. Next we have multi-tape sorting algorithms. Multi-way merge sort is commonly used to combine sorted runs from multiple tapes efficiently. Parallel merge algorithms can operate on multiple tapes simultaneously to accelerate sorting. These algorithms exploit tape parallelism to reduce total sorting time significantly. The next is hardware support of parallelism tape sorting. Multiple tape drivers can be operated simultaneously to enable real parallel data transfers. Modern tape libraries support robotic mechanisms to automate tape handling and parallel access. Hardware improvements have been key in enabling effective parallelism in tape systems. Software techniques for parallelism. Scheduling algorithms coordinate multiple tape operations to maximize throughput. Buffer management ensures data is efficiently streamed between processing units and tapes. Software optimizations help overcome latency and sequential access limitations. Parallelism and data transfer bottlenecks. Despite parallel operations, data transfer rates can still limit over performance. Effective overlap of computations and data transfer minimizes idle times. Strategies like prefetching and buffering are crucial for maintaining high throughput data parallelism. Performance metrics in parallel tape sorting. Throughput measures the amount of data sorted per unit time. Speed up compares the performance of parallel algorithms against sequential ones. Scalability access how well the parallel system performs as more tape drives are added. Benefits of parallel tape sorting. Significant reduction in total sorting time for large datasets. Improved utilization of tape drives and processing resources. Enhanced capability to handle ever-growing data volumes efficiently. Next one is limitations and bottlenecks. Hardware costs can escalate with increase in number of tape drives. Synchronization overhead may reduce the effective gains from parallelism. Sequential nature of tape still imposes fundamental constraint on maximum achievable parallelism. The next one is case studies and real-world examples. Large-scale data centers utilize parallel tape sorting for backup and achieving. Scientific reason project process massive datasets with parallel tape techniques. These applications demonstrate the practical benefits and challenges of parallelism. So here we can see the some of examples of data parallelism, model and data parallelism, expert and data parallelism, export, model and data parallelisms. Next one is future trends in tape sorting parallelism. Integration with high-speed robotic tape libraries will facilitate greater parallelism. Advance in tape drive technologies may reduce latency and improve bandwidth. Hybrid storage systems combining tapes and disks can leverage the strengths of both parallel processing. Comparison with other storage media. Unlike disk-based systems, tape systems excel in sequential data access but lag in random access. Parallelism techniques are more mature and effective in disk and SSD systems. Combining tape and disk storage can optimize overall data processing workflows. Design considerations for parallel tape sorting systems. Balancing load across multiple tape drives is critical for maximizing efficiency. Maximizing data movement and transfer overhead improves system performance. Robust error handling and synchronization mechanisms are necessary for reliable operations. Implementing parallel tape sorting in practice, system architects must consider hardware, software, and workload characteristics. Simulation and modeling can help optimize parallel strategies before development. Continuous monitoring and during the and tuning are needed to maintain peak performance. A summary and key takeaways. Parallelism significantly enhances the efficiency of tape sorting for large datasets. Both hardware and software involves are essential to overcome tape storage limitations. Ongoing developments promise even greater performance gains in future tape sorting systems. So the differences are Smith-J parallel algorithms for tape sorting, Journal of Data Storage LE Liar Patel S 2009 Advances in Tape Sorting Techniques. So these are the references where I took this information and gathered to explain it in brief. Thank you for giving this opportunity.